And it has to do with something, actually, let's do this. Let's review a little bit what we did last time, and then lead it up into something you need to do some of the homework that we haven't talked about yet. So a little review. So 11% of the general population is left-handed. So you got to excuse me for always using this, but it's a good example here. Which means how many are not left-handed? 89%. I like it. Cool. So if I ask you a question like, okay, so we pick 10 people. Accompanied to music. Pick 10 people. Have them tell us if they're left-handed or not. Because they could say, I'm ambidextrous, I'm not left-handed. We're like, whatever, you're not left-handed, fine. So pick 10 people. What's the probability that exactly one is left-handed? That's the first problem we'll do. So I am desperately hoping, I haven't even written what the real formula looks like yet, because very often the formula makes things look worse than they really are. And that's not algebra's fault, that's not math's fault. It's just that it's trying to capture the most general situation. But in each specific situation, the formula is pretty damn simple to set up, and hopefully you guys either already agree with me or agree with me very soon. So what are the parts I need to identify for this problem? Or what have I already told you here that you can give a variable name to? I like it. So I know, well, not x, but n. So n is 10. What are these two things?
P.
Yeah, what's p?
11%.
Yeah, so 0.11.
0.89.
0.89. I like that. I already got a big sigh, only a few minutes in. Here we go, statistics. Be really careful about when you plug this in the formula, it's got to be a decimal, right? 11%. The percent symbol is something that humans made up just to make things easier to look at. Math says, that's nice for humans, I need the actual freaking number, which is the decimal. If you plug 11 and 89 in your formula, you're getting some weird-ass answers. 1,080% chance, no, that's probably wrong. And then for this specific problem, what's that number there? Somebody remember? What variable name do I give that? You guys remember? I said it really quickly last time, so I don't blame you. It's x. X is the number of successes that we want. The number of successes. How are we doing so far? Is that cool? So you want to pretty much always identify those four things. These three things are going to be for maybe a few problems, and then each problem is going to have a different question, exactly one success, exactly two successes. So x is going to change. That's why we use x. It's the variable, right? So how do I set this problem up? How does this probability of 1, how does that thing start off? Good. I got 10 people. I want to choose one of them to be left-handed. So how many of these people do I have? 1. That's crazy. And then how many of these people must I have? 9. The rest. Now, if you were here last time, you're sitting there saying, what the hell is going on here? Understood? So watch the video, come see me, something. I'm not going to redo the lecture. So let me show you one more time how to do that in the calculator. So get a little quicker. Let's see if you guys can see this. That's the computer up. Okay. That's probably going to be gruesome. Oh, you can sort of see that. All right, I can live with that. Whoa, did the lights just go down? Yeah.
I did.
Did it really? Oh, you did? You freaked me out. They install like mind control. I'm like, only the lights went down. All right, that was weird. All right, so where's that choose dude? So here's the 10. Where's the choose dude at?
Math.
Yeah, go to math.
Then
Probability.
NCR.
Yeah, the choose dude. 10 people, I want to choose one to be left-handed. So how many .11s do I want? Well, that was 1. So I can make it very specific there. That's, doesn't need to be in there, but there it is. That's the part you can't really see too well. Oh well. You see, are you alive yet? No. You see, it's not even alive. And then times .89 to the rest, to the 9th. Okay, so we get exactly one left-handed. This probability is going to be 0.3854. So almost 39% chance that if I pick 10 people randomly, exactly one of them will be left-handed. Can I with you? Now, a little more interesting question. Exactly one is almost silly to ever ask that question. What's more likely to be asked is something like, what's probably at least one person is left-handed? Kind of with me? And let's get closer to, and I don't know if all the rooms have this, but normally the rooms have a few left-handed seats. I don't know if you've seen that on campus. I've seen it every now and again, but not as much recently. So I think all the left-handed seats have been procured somewhere. But very often, if you say that there are 50 seats in the room, what's the highest probability for the number of left-handers that are going to come in? And then you're going to make sure you're going to have at least that many left-handed seats in the room. Does that make sense? That's exactly the kind of problem you can do with the math we're learning right now. Real-world, immediate application. Not something you got every day from algebra. Algebra is very useful, don't get me wrong. I'm a math dude, I love algebra. But this is like, you can use this, bam, right in the real world. So what about, how do I do that then? Probability of at least one left-hander.
It's 1 minus.
Yeah, good. Because do you realize, how would I answer that question directly without adjusting anything?
1 minus.
What's at least one mean?
That's not that's
Whatever it is.
No, don't go there yet. But at least one means what specifically exactly itself? At least one means 1 or 2 or 3 up to 10, right? So if you really want to answer this question directly, you'd have to do probability of 1, we got that, plus the probability of 2, do the whole thing again, plus the probability of 3, do the whole thing again, plus probability, okay, so I'm showing you why the hell you don't want to do that, right? If the opposite situation has fewer calculations, hell yes, I'm going to do 1 minus the opposite situation. It's quicker. So the opposite of at least 1, of course,
9.
is
9 choose.
none. Thank you. Okay.
None.
So this will be 1 minus the opposite. So what does this look like in this form?
0.
Careful. How many people do I have?
10.
10. And I want to choose
0.
none of them. So how many left-handers do I want? None. So how many not right, but just not left? 10. Let me stop right there. You guys with me on that? There's the two ideas of, and this is in general, this is not just for at least one. This is for any situation where the opposite situation has fewer calculations. Hell yeah, I'm going to do it that way. So this situation by itself has 10 calculations. I got to do 1, 2, 3, up to 10. The opposite situation has 1 calculation. Hell yeah, I'm going to do it this way. It's only 1 calculation. So what do you get for this? Computer has finally joined
6.8.
the discussion.
0.6882.
Catch up to it. So if I do 10, well, what do you think 10 choose none? How many ways, if I have 10 people, how many ways can I choose none of them?
1.
One way. I choose none of you. Right, and then that's it. So this is 1. What's anything to the 0 power?
1.
1. So the only thing that really matters is that guy. For this, and you're not going to be wrong if you put it all in there, but the only calculation I have to do for this problem is 0.89 to the
10th power.
Yeah, point. So it's 1 minus 0.3118. So it's 0.6882.
689%.
Roughly. Yeah. You guys kind of with me? So if I have 10 people coming over, there's a really good chance that at least one of them will be left-handed. So I probably should have one, if not two, left-handed chairs out for them. Does that make sense? That's the kind of planning you can do. It's the kind of thing that statistics would help you plan for. Okay, cool. So, and of course I chose, I'm silly. All right. Well, that's a good little review of that. Let me make a better example. It's going to lead into the thing I want to show you. So how are we doing there so far? So decent. Even if you weren't here the other day, you kind of start to see how things fall into that formula. You still want to look the formula up. By the way, here's what the formula looks like. And let me see if you guys get the whole thing. So it's n choose x. That makes sense. The total number choose how many I want. What was this in symbols? The 0.11 was the peak. And how many successes do I want? Well, I just said I want x of them, right? Now here's where people freak out. How many q's do you want then? N minus x. It's always got to be the rest. If you have a total of n and you take x away to put here, how much is left? N minus x. You actually got that exact situation in algebra, believe it or not. 5 hours total, x hours going there, 5 minus x hours coming back. All right, that's the kind of problem you saw then. So this will be q to the n minus x. Do you see what I mean by the formula makes it look harder than it really is? Okay, cool. So that's the formula we've been using. The book, real quick, the book uses a factorial equation for that they get from section 4.6. This is one place where you don't lose anything by just pushing the buttons. Let the calculator count it for us. So I don't mind just using this instead. That's the button on the calculator. Just to count how long that list is. Who cares how you get it? You just want to know how long the damn list is. Yes, sir?
What is the equation for that?
Say again?
What is the equation for choose?
Oh, so if I have n choose x, let me see if I remember. It's been a while. This will be, now I'm going to talk myself into it.
Henry, look at the book.
Pretty sure it's that one. Let's see. 4.6. Yeah, good. All right. So that's the formula you're going to see in the book. And I just say we're going to replace that with the calculator procedure. Cool. That factorial, real quick. So if you see that, it's not 5. Does anybody know what that? They're like, there's punctuation in mathematics, but anybody know what that symbol means?
5 times 4 times 3 times 2.
I love it. So it's 5 times 4 times 3 times 2 times 1. So 120 factorial will be 120 times 119 times 118, all the way down to 1. So it grows pretty damn quick.
That's pretty exciting.
Totally. Oh, that's pretty good. It's almost as good as mine. All right. I love these things. You gotta straighten the wall. So let's do a really simple little problem, and I want to show you how it relates to. If you start to look at the homework, they talk about a table in the back of the book, and actually it's perfect because I was going to do the table today to lead us into chapter 6. If I had a situation where, let's say, 40% of people like butterscotch. Personally, I would not choose it. But how many of you guys like butterscotch? Anything? Butterscotch? Anybody? All right, so maybe 40% is not true, but we'll just stick with it. 40% of people like butterscotch. Even fewer stat students like it.
60%.
I want to know if I pick 12 people, what's the probability that exactly 9 of them like butterscotch? Let me shut up for a minute. You guys don't say anything. Try to set that problem up. So now you can set up the equation. You have 12 people. Yeah. I like it. Yep. Yep. All right, so let me try to catch up to you guys. What's N?
12.
12, good. What's P?
9.
9. Point
Careful.
4.
P is 0.4. That's a probability of success. Q,
0.6.
0.6. I like it. That must be the rest, right? Failure is 40%. The success rate is 40%. The failure rate must be 60. And then in this case, X is 9. So now I can set this thing up. I got 12 people. Choose 9 of them to do this. So how many do this? The 9 people you chose. Right? So it's a little repetitive. And then how many of these?
3.
3.
0.01246.
So say it again, sorry.
0.01246.
0.01.
246.
246?
Yeah. 4.
2.457 is what I got.
Let's see. We got a controversy. So we got 12. Choose 9.4 to the 9th. 0.6 cubed. 12457. Yeah. Okay. So 1.25%, just about, roughly. Okay. All right. Now watch this. And this is we're not going to really use this too much, but it is a nice, quick visual that's going to lead us into the next section a little bit with some help. On page 603, I think it is, roughly around there. 601. You got a table called binomial probabilities. And you see how it's set up. I have n going from 2, 3, 4. Now, of course, if n is 3, the most successes I could have would be, if I have 3 people, how many of them could vote for me at most? 3. So that if I have 3 people, I can have 0, 1, 2, 3. So as you go down, these get longer and longer because you got more and more chances to have something happen. So for our situation, n is 12. So if we come over to the bottom of page 602, n is 12. Can you see all the way over? Yeah, that's plenty good enough. Of course, what sucks is p is 0.4. Do you see here's 0.4? Oh boy, here we go. 0.4 is here. The one that starts with 0.227. Are you guys with me? Or no, it starts with, where'd it go? 0.002. Am I with myself? Okay. So that means like the probability that 3 people would like butterscotch would be 0.142. Right? It's probably that 9 people like butterscotch. We got 0.0125. What do they get? Am I going the right? There it is. 9 is right here.
Yep.
0.012.
Yep.
Kick ass. Remember, the next number really was a 4, so you're going to round down. Right? So this chart, this table has a lot of problems. It only goes up to 15. Right? It only goes up to n equals 15. The minute you have 16 people, the table's not worth anything. The probabilities, do you remember now? Do you see why I didn't like the fact that I picked a left-handed problem to do this? Because the left-handed problem has a p of 0.11. Do they have a p of 0.11 at the top?
Nope.
Nope. So you're screwed there too. So the table has a lot of flaws. It's only good for certain situations, right? People at home, there it is. But one good thing about it, look for example at 14. Unfreeze. There we go. So we can get this in there. 14. Stay. Okay. Well, that's good. All right. That's really good. So if you look at the column that's probability of 0.5 for 14. Probability of 0.5 should be this one. Is that right? So look at the probability of 0.5. Go down to 14. Don't you get these here? Now, could you imagine creating a histogram? And the heights would be related to these percentages. You with me? We've done that before. So like the 0 would have no height, really. The 1 would have a height of 0.001 and so forth. What shape would this take? Bell shape. Why? I like it. Symmetric. I like it. It's folding. And also it goes up to a peak and then back down. And the really cool thing is right in the middle is this one. And what should be, so for example, what situation might this cover? The probability is 50, so it's 50-50 chance. I'm doing something 14 times. So what's a real life situation that might be modeled by that? All right, cool. All right. So if I flip a coin 14 times, how many heads would you expect to get on average? 7. So that's the expected value. That should be the highest probability, right? That's the one that should occur the most. And sure enough, it's the highest probability. And it goes exactly down the same amount on both sides. So this should look very normal. And the really nice thing is, I've got that picture here. What do you think 0's plus means? What do you think 0 plus means?
0.0005% chance.
Yeah, it's going to be less than something that'll be rounded to 0.001. It'll be less than that.
Another reason tickle's useless.
Exactly. If you get enough of those 0 pluses in a row, they're going to add up to something. So your answer is going to be always less than it should be. Sure. All right, so this is my attempt at transitioning into Chapter 6. Chapter 6 is going to be related to strictly normal distributions. You could tell that from the title of Chapter 6. What do we know so far about normal distribution probabilities? All right, that's an interesting phrase, not one you hear probably anywhere else than here. What do we know about normal distribution probabilities? Okay, the curve itself is symmetric. I enjoy that. So something more specific. If I go out 1 standard deviation in both ways, I catch how much of the data? 68%. Go out 2 standard deviations, 95%. 99.7, you almost catch the whole damn thing if you go out 3 steps. How far do you have to go out to catch it all? Well, come on. You have to go out to infinity in both directions, theoretically, anyway. Right? But that's enough of that. You almost catch the whole damn thing within 3 steps, which is really sort of like going with the height. Theoretically, the height could go forever. Now, that's obviously wrong. But within 3 steps of the average height, we catch about 100% of the people, just about. There's very few people that are taller than 7 foot, whatever, and very few people who are shorter than 3 foot, right? So we catch almost everybody within 3 steps away. So here's, first part here is just a little review real quick. Try to do those first 2 problems that I have up there. So these 2 problems here. Number 2 is going to test your understanding of something we talked about earlier. Catch up to you. I think most of you should have number 1 done or almost done. Number 2 might be giving us some trouble. I don't know. What's N, P, and Q for this row? What's N? 14. P and Q are
0.5.
0.5. We're assuming it's a fair coin. So the probability exactly 9. How would you set that formula up?
9 times 0.5 is 14.
Yeah, 14 choose 9. 0.5 to the 9th. 0.5 to the 5th. Because there's got to be a total of 14, right? So I've got 9 successes, 5 failures. So if I do that formula, what do we get?
12.22%.
Sounds about right. So we get 0.122, something else, about 12.2%, just about. Is that cool? Is that what you guys got?
Yeah.
I'm just trying to do a percent symbol there. Okay. Now what about number 2? Who's got a way to do that?
1 minus the probability of 9 minus the probability.
Yeah, the worst way to do it would be do 2, 3, 4, 5, up to 14. Screw that. I don't want to do all that work. Thankfully, I don't have to. What's the opposite of at least 2?
1 minus
1 and none. I love it. So it'll be 1 minus none
minus
1. I've got to subtract everything that I've left out. So what's the probability of none? What would that look like? Say again? Sorry? 14? Choose 0. So 0.5 to the 0. 0.5 to the 14. So that's probability of none. Probably 1 would be 14 choose 1.
0.5 to the
0.5 to the 1. 0.5 to the 13. Cool. And you can actually put it in your calculator exactly like that. Have you guys got that? I want to show you what it looks like in the calculator. Here it goes. So if I do this here, it'll be 1 minus. Now hopefully you guys remember about the zeros. 14 choose 0 is 1. 0.5 to the 0 is 1. So all I have to do is 0.5 to the 14. That's the probability of none minus 14 math choose 14 choose 1 times 0.5 to the 1 times 0.5 to the 13. So do you get that? 0.9991 basically. Do you get that? Oh yeah. You got that, Jeff. It's all good. All right. But I just want to show. I mean, you could put it in. You could put the formula, this whole formula in 1 minus, and then start doing the choose thing. You can put it all in at once, because there are mistakes that happen when people try to do parts and they try to put it back together. Sometimes those parts don't go back together correctly. So, poor little dude. Oh, there he is. We got, for this guy, we got 0.9991, just about.
I have a question.
Yes, sir?
You wouldn't have to include 2, since it's at least 2?
So, I am including 2 by subtracting from 1 the things I left out. So in order to include 2, I don't want to subtract 2 out. I want to subtract the stuff that I don't include. So if I would have said the probability more than 2 heads, but I had to do 1 minus probably none, minus probably 1, minus probability of 2, I would have to take that out because I'm not going to include it. So I'm subtracting the stuff I'm not including. Good. Because that's the opposite, right? The opposite of at least 2 is none or 1. Okay, maybe. All right. So real quick, let me show you something nifty in the calculator. It's on the calculator handout that I gave way back when. Let me show you the shortcut for these things. So the number 1, the probability of exactly 9 heads. Here's the shortcut. You ready? It's on your handout. If you go to second vars, if you don't have a calculator and you want one, there are some up here. Go to second vars. That'll get you into distributions. You see how it says DISTR up there? DISTR, short for distributions. You'll see some interesting, you got some stuff about normal stuff, right? You got some weird ass shit down here. And then, did I just say? I guess it. Here's where you got the normal. The difference between those two. So we're doing right now a binomial probability problem. So there's 2 options here. The difference between those 2 options, the first one is binomial PDF. That's particular value. If you want a single value, I want exactly 9 or exactly 2 or whatever, I'm going to use that one. Part B is binomial CDF cumulative. So if I use that one and I put the number 9 into it, it's going to do from 0 up to 9. It's going to accumulate all the way up. You guys with me? So the P is particular for a specific value. C is cumulative up to a specific value. So if I want to do number 1, the one exactly 9 heads, I would choose the particular one. And here's the input. What do you think the calculator has to know to be able to set up the formula that I need? What's the calculator have to know? It's definitely got to know N. It's got to know X. And it's got to know the P. Do I have to tell it Q?
No.
Hell no, it's the calculator. It should be able to do 1 minus the damn thing. So the input for this is NPQ with some commas in the middle. There's punctuation. So I have N is 14, right? 14 times. Probability of success is 0.5. And on the first problem, I asked for exactly 9 heads. So the success is X is 9. Enter, I get the 0.122, blah, 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 that we got earlier. Cool. That's the answer we got on number 1, the first part. What about to do the second part, the at least 2 heads? So at least 2 would be 2 and up. Binomial CDF is hardwired to do from 0 up to whatever number you put in. So we figured out the opposite of this is 1 minus probability of 0 or 1, right? So up to 1. So this part, binomial CDF could do. So if I do binomial CDF, and I do the same inputs that I did here, except I'm going to put a 1 in there for X. it'll tell me this number, and then I can do 1 minus that. So if I do 1 minus, second bars to get into distributions, binomial CDF, then I can do 14.5, and now I want to go up to 1. I better get the 0.9908 that we got. Yeah. Ooh. Thank God. Now, to tell you honestly, if you don't understand binomial CDF, binomial PDF, you absolutely do not have to pass this class. This is purely so you can check your work. This is not a way to do your work. If you just write on a quiz, showing me your work is not, this is what I put in the calculator. That is not showing me your work. I must see this. I have to see that formula set up. Now you can always check it. If you understand this, you can check your work very quickly doing this kind of thing. You with me? So if you really don't want to know that at all, that's cool by me. You got something even better. You got the freaking formula. What's the calculator do to do that? It does this. So if I do this, I'm just doing what the calculator is doing. It's not a big difference. But I need to see that. You with me? There's only one chapter in this whole book where you can get away with, well, this is what I did in the calculator. Right? And that's the last chapter in the book. Yes, that we're going to talk about anyway.
How'd you do the comma again?
Oh, comma is right above number 7.
How'd you do the up to the exclamation mark one? So the last one on the binomial CDF.
Oh. So binomial CDF means up to whatever I put in there. So you don't know how to show you the whole thing anymore. There we go. So if I'm using CDF and I put a 1 here, it's going to add 0 to 1. If I put an 11 there, it's going to add 0, 1, 2, 3, 4, up to 11. It's going to add those together for me.
Mine came out different.
No.
I didn't do the 1 minus this one.
Oh, okay, yeah. Now do 1 minus that. Cool. Okay, how are we feeling so far? So you got a calculator approach that you don't even have to know. Right? Some of my colleagues teach only that. That's crap. Sorry to be so blunt. But if you're having this guy do the work for you, you're not learning shit. So if anybody's taken stats before and I start doing something by hand that you've done on the calculator before, that's nice. You know how to check yourself, right? I need to see the freaking work. Okay. It's just that every now and again somebody says, well, my teacher told us we just have to do this. Well, that's the other freaking teacher. Right? They're not teaching the class. They're not going to give you a grade. Okay. So continuing on, some other little formulas we learned last time was for the mean. So we should already know this. We calculated this earlier. What's the average number of heads if I toss? Flip a coin, yeah. It'll be 7. It'll be 14 times 0.5, 7. So the average number of heads I should get would be 7 if I flip a coin 14 times. The standard, what's this really represent? What is this?
Variance.
That's not the standard deviation, that's the variance. Cool. So if I do n times p times q, yeah, I get 3.5. So how do we get the standard deviation then from that?
Take the square root.
Square root of that. Square root of 3.5 is?
1.8708.
1.87.
708. I was close. 1.871. Rounded. Cool. How are we doing so far? So almost every distribution we learn, we want to know how to find the mean, and we want to know how to find the standard deviation. Because if I can do that, I got like empirical rule, I got Chebyshev sitting there, and we got a lot of other stuff that we're going to learn today that I can use those for. Right? So how do I get this? Now here's, some of you guys have read this in an earlier session. I haven't even talked about it yet. But I think I might have talked about this before. What's the minimum expected number of heads? I think I did talk about that last time.
Subtract 2 standard deviations.
I love it. So min and max would be within 2 steps away. That's the number of expected. 5% we define as being unusual. So how far do I have to go out to catch everything except the most extreme 5% to go out 2, because what's within 2 steps of a normal?
5%.
5%. So that would leave the 5% outside. So that matches both ways. 5% is unusual. 2 steps away has 5% outside. They both mean the same thing. Both mean unusual. So what's the minimum expected number of heads? I would take the mean minus 2 steps to see where that is. So that would be 7 minus 2 of these things, which is whatever the hell that is. Is that 3.3?
7.5
Yeah.
or 7.2.
3.3?
You round into it. Yeah, you round into the first.
All right, I'll take that. About 3.3. And then the maximum would be 7 plus 2 of these, which is going to be roughly 10.7.
10.742.
I like it. So if you flip a coin 14 times, the minimum number of heads you would expect would be 4. Do you guys see where I came up with that? If you get 3.3 heads, I want to see that. That's neat. What happened on that 0.3 time? The coin landed at an angle, showing the head mostly. 30% of the head was showing. No, that's freaky. So the minimum I expect would be about 4. So if I got below 4, that's a little unusual, right? It's like, whoa. And if I got above 10, that would also be unusual. You guys kind of with me? That's how you interpret that. Cool. Sort of like what we did last time when we had the person that got 8 right. If you missed last time, you missed an ESP test. Right? We had one person in here that I have to wear my tinfoil hat around because they can read minds, but they got 8 right out of 20 when they were guessing something. Most of you guys were here. So that was unusually high amount of correct. Okay, so here's where we finally get to see how this connects with chapter 6. So this is actually, this is old news. This is chapter 2, right? Graphing a histogram. There's what we used to call a relative frequency table, relative frequency distribution. Now we know that these can also be seen as probabilities, right? So 2.2% of the time I'll get 11 heads. So that's the probability of getting 11 heads. How are you doing so far? Okay, cool. So notice if I have the graph of something, how do I find probabilities? Actually becomes an area question. Let me say that again. If I have the graph of a probability situation, a question about what the probability of something is becomes an area question. What's the area of this rectangle? How wide is it?
1.
Good, because that's from 5.5, 6.5. So that's a width of 1. And how tall is it? 0.183. So the area of this rectangle is 1 times 0.183. So the area is 0.183. But what is 0.183 also?
The height.
The probability of 6, right? So the thing I'm desperately trying to get you guys to understand is, when you're talking about probability, if you can graph the situation and find the area for each situation you want to talk about within that, that would be the probability of that. So here's another example. Here's a very simple, this is what's called a uniform distribution. And distribution is one of those words that makes you sound drunk, so be careful. Talking about distribution. So uniform, that. What do you think that means, uniform?
It's all the same.
It's all the same. I love it. Right? So a uniform distribution, no, I can't say it, would look like a big triangle. Good job. Big rectangle. Right? So maybe this would be oops, we do like this. Change it just a little bit if you're drawing this at home. 1 to 6. 1, 2, 3, 4, 5. That's roughly good. 6. I like it. So this might represent something like rolling a die. You with me? Got to get my verb correct. So trying to roll a die. So each one of these has what probability of happening?
Equal.
Good. And what is it? 1/6. It's got a 1 out of 6 chance. So sure enough, what's the area of the whole damn thing? What's the area of the whole rectangle?
1.
1. And why does that make sense?
Because everything's the same.
Because areas are probabilities, and if I take the whole probability, I should get 1. If I add up all the probabilities, you with me? So we start to see how these connect. The area of the picture versus the probability of the situation. They actually end up being the same damn thing. Don't forget the rectangles. That's all it is. So if I want to know what's the probability that is from 2 to 4, let me make it a little more. So I get a 2, a 3, or a 4. I could just find the area of this. And this is where I got to be careful when I do this kind of problem. I got to make this a little more specific. I know I'd run into trouble just trying to come up with something on the run. Okay. That's a little better. So 1 has a 1/6 chance. So if I want to go from 2 to 4, what would the total area be? Yeah, it'd be 1/6 plus 1/6 plus 1/6.
3 out of
So 3 out of 6.
2, 1/2.
1/2, exactly. So 1/2 chance of that happening. To get a 2, a 3, or a 4. So forth. Now, the problem I run into is I'm trying to create a uniform distribution out of a situation that is discrete, right? Is there any such thing as getting a 1.3? If you can, let me see your die. That's like Dungeons and Dragons to the next level, right? Okay. That's a uniform distribution. Its areas are simple because they're all rectangles. Same thing as this is not uniform, but its areas are still rectangles because it's just really a histogram, right? I could even have situations where I have a triangular distribution. So if I want to know the probability from this to that, I just find the area of that little triangle. You guys kind of with me? So let's get into what we're actually going to do the most of. There are a few uniform distribution problems in the first section of chapter 6, and then we just shoot the hell past that. This should be pretty quick, just finding areas of rectangles and realizing that it's probability. So what we really want to talk about is the normal distribution. And let me just freak you out for a second. Why not, Jeff? You do that all the time. So, of course, we know a normal distribution. We know what it looks like. We've already talked about it a lot. So there it is. Right? So that's amazing. Good old bell curve. Yay. So why would the triangle be really simple? If I had a triangular distribution, I want to find the area. Just find the little area of the triangle. Why would that be simple? Because we know the area formula for that, right? So here's the problem with this. And this is why you thank God. How many of you guys have had calculus? Anybody? Oh, sweet. A decent number of you guys. Do not worry. You do not have to know calculus for this class. But if you have taken calculus, you will understand what I'm about to say a little bit better. The formula that describes this curve. Here it is. This is the only time you have to look at it if you don't ever want to look at it again. That's the formula that describes this curve. Whoa. As you absorb that. What do you see in there that's familiar? Standard deviation.
Mean.
The mean.
Exponent.
And what's that x minus mu over sigma? What is that really? Who remembers what that is? It's given a name. It's the... What did Zorro do on the wall? Is that a weird question? Make a z. That's a z-score, right? Z is x minus the mean divided by standard deviation. Right? And you all know e, and you all know pi, and all that kind of stuff. So somehow that formula describes a normal curve. In fact, if you picked values for mu and sigma, you could put this in the graphing calculator, and it would graph you a normal curve. It's really kind of neat. In fact, now I just said that I want to do it. So if you want to, you just watch. Somebody help me out. Give me a value for the mean. 8. I love it. Now give me a value that makes sense for the standard deviation. Don't make it 20. Make it
4, 1.2.
Do it. All right, 1.2. I like it. Cool. Are you ready? So this formula that I certainly don't have memorized would be E. Where'd E go? There it is. E to the negative 1/2 x minus the mean, which you said was 8, divided by, oops, I'm leaving something out. Just watch. It's neato. Divided by standard deviation, which was 1.2, right? Squared. And that whole thing divided by the standard deviation times the square root of 2 pi. Oops. Get out of there. Wow. Okay. So you can see how really tiny it is. It's going to be centered around 8, right? So let me kind of zoom in a little bit. Let's make x min 0 and x max 16. So the 8's right in the middle. Is that cool? And it looks like I probably want to make let's make y min -1, y max, let's make it 0.5. Let's see what happens. All right, that's better. Neato. Okay, so I could zoom in a little more. Crap, but there's the shape, and you can pick whatever, and it's centered around 8, right? And if you go out 3 steps, you will capture most of that picture. Are you kind of with me? And if you understand it all, e to the negative power, does that ever go to 0? Does anything to a negative power ever go to 0? No, it's asymptotic there. I don't know if you guys remember that. It's asymptotic there. So theoretically, this never goes to 0. In the real world, you eventually have nobody who's 10 feet tall. The math is going to say, well, there's a 0.00003% chance. No, screw it. It ain't going to happen. Right? Well, you never know, actually. Okay. So, I don't want to lose this connection then. If I could find a way to find the areas between two things in there, that would be the answer to a probability question. So for example, the mean is 8. So if I want to find a way to get the area between 9 and 10, that area would equal the probability that x is between 9 and 10. You guys semi with me? Because remember, area for a visual of a probability distribution equals probability. That kicks ass. So thank God, now those of you with calculus backgrounds, what is it that you do to get area? Integrate. So if you somehow integrate that function, you'll get all the areas that you want if you integrate between them. So thank God, the rest of you haven't taken calculus. You know, like, I know that word integrate, but I don't know what the hell it means with math. Don't worry, you don't have to know. That's what we have this for. Okay. So some of you guys might have your insert still. If you don't have your insert still, then the very back of your book, very back of your book, is the z-score charts. Now hopefully your book, again, is in better shape than mine. Right? It's being barely held together. But the first thing I want to do with this is point out what this thing does. Zoom into the top here a bit. Okay, so what kind of distribution does this work for? Normal. Good. So if you don't have a normal distribution, can you use this chart? No. Good. Right? Will some of you still try to do it later? Yes. This chart only works for normal distributions because this is basically, like I was saying earlier, this is the empirical rule just pumped up. This is the empirical rule to the next level. Right? Empirical rule, I really just know within 1, 2, and 3. Now notice also, if I look up a z-score, like if I looked up a z-score of 1, what the hell happens? What is all that crap over there? What do you think? If I want exactly 1, that's 1.00, for example, right? You can put as many O's as you want to, but that would be 1.00. If I wanted 1.01, I'll go here, 1.01. So across is the second decimal place. You with me? Okay, good. I think you're with me. So this is a very strange, it seems to be a strange way to do it, but if you think about it, it's the best way to do it very effectively and get it all in there. Otherwise, you got this huge ass thing like a map, and you're just unfolding it to see the z-score. This is not a bad idea. Now, of course, that has limitations. I'm going to show you how to do this in the calculator also later. But there are reasons why I want you to still use this table to find probabilities, at least at first. But notice if I had a z-score of 1.013, this can't be that specific, can it? So we do lose a little bit, but I'm okay with that for a while. So let's see what this really, really means. Let's do a problem based on empirical rule alone. So if you guys remember this. And then we'll check it and see if we get the same answer in the chart. If we don't get the same answer, we can just throw this damn thing away and watch movies for the rest of the semester. Right? Because you're all like, please don't. So somebody remind me, within one step was how much? 68%. So how much would be, let's do this. How much would be down here? Beautiful. If there's 68% in there, there must be how much outside? 32%. So how much on that side? 16. It cuts it in half because it's symmetric. So it should be exactly or close to 16%. Empirical rule kind of rounds the numbers. So whatever you get should round to be 16%. So in this chart, so how does that question really look like symbolically? That would look like this. Probability x less than -1. Actually, maybe a little more specific. These are all z-scores we're talking about right now, so probably z less than -1. What are we doing so far? Not too bad. Somewhere in the middle. Okay. So the chart is built to answer questions about below the z-score you look up. So that leads to problems if you want to find between two z-scores, or if you want to find above a z-score, you're going to have to do something to adjust. But if my question is below a z-score, I'm good. So sure enough, I want below the z-score of -1. So if I look, now thankfully there's a negative side. Somewhere, you think it'd be on the other side. There's a negative z-score chart. Wow. So when I'm on the negative side of things, so if I look up a z-score of -1, so look up -1.00, what do I get? Which rounds to what percent? 16%. Cool, right? So you can find all the values we knew before from empirical rule. They're, of course, all in here. It's just that this, thank God, is more useful than the empirical rule. Does everybody's height fall exactly in an integer number of standard deviations? Oh, hell no. So if I want to know the probability somebody's taller than let's do that problem. This is good. Let's see how this works. Let's do a real problems are always nice. So if I had, remember the mean height for men was 69 inches, standard deviation was 2.5 inches, I think, or it's 2.8? Something like that. And I want to know the probability that, and these are normally distributed, right? So if I don't say it's normal, you can effectively say, and I ask you a question about probability, you can say, can't do it. Next. Because you can't use this chart unless it's normal. So we know these are normally distributed heights. And I want to know the probability some dude is less than 64 inches tall. Maybe so less than 5'4". I don't know, what percentage of men are less than 5'4", or what's the probability that some dude is less than 5'4"? They both mean the same thing. What do I need? before I can use this chart? What is the name of this chart?
Z-score.
So what do I need before I can use this chart?
Z-score.
That's crazy. And how do I make that into a z-score?
You subtract
What's the z-score formula?
negative E negative.
No, God, no. Not that one. What does the z-score tell you? What does the z-score tell you by itself?
Standard
What about standard deviations?
The two standard deviations.
What percentage? Or,
Nope. Z-score by itself can't tell you percentages.
How much standard
Z-score tells you the number of
steps away from
standard deviations
away from the mean
from the mean
to the
to the
value,
data point.
the point
Right.
where you.
So I get a little depressed inside. So z-score tells me from the mean to the data point how many standard deviations fit in there. Right? So it's a measure of standard deviation. It's actually a measure of how far away from the mean I am. It's a relative measure. Because if my standard deviation is 0.3, then I don't have to push this over very far to be far away. But if my standard deviation is 1,000,000, I gotta go way out there just to get relatively far away. Because every step would be huge. So it's a relative measure of distance. This is how I measure distance in statistics. And why is distance so important? Because I know if I go 1 step, 2 steps, there's going to be less and less percentage out there. Less and less people who are taller than that or shorter than that. So what does the z-score look like for 64 inches? How do I put this formula together?
64 minus 69
Good, 64 minus 69
over 2.5.
over 2.5? Yeah, almost. -2. And of course the negative just tells me that the score is
Negative.
below the mean. I like it. So if I draw this picture from the beginning, it looks like, what goes right in the middle?
69.
69. And I'm interested in the point 64. Shade in the area that you want. So I want the area that's
Less.
below there. I like it. This is a little more than a suggestion. Because the people that don't draw the picture are the people that are going to make the most mistakes. So if you choose to make mistakes, there's not much I can do for them. But I highly recommend you draw the picture. Sort of an anchor to make sure make things. If I get an answer of 80%, does that make any damn sense? No. But the person that doesn't draw that is just going to put it down and go, I got a number, yay. They're not going to realize they must have made a damn mistake. Does that make any sense? This is less than half, right? This should be something tiny. So in z-scores, here's a really... When I learned statistics, my teacher made us draw one picture with these scores and then a whole other picture with z-scores, and that's kind of stupid. Nothing against Mr. Pearson. That's my old stats teacher. But below here, I could just put, what's the z-score for 64? -2. What's the z-score for 69?
0.
Beautiful. The mean is 0 away from itself. So it looks like a standard problem would be, they give me some, what's called a raw score. It's called a raw score because I haven't processed it yet. So they give me some raw scores. It could be heights, it could be years of life for a turtle, it could be whatever. I process it into a z-score and then I can immediately look it up as long as I'm working with a normal distribution, right? So now that we got -2, if I look up -2 on the chart, will I get my answer? Because what's the chart always tell me? The area that is below the z-score I look up. So sure enough, if I look at -2, that's exactly the area that I want. So if I look up -2, -2.00, I get 0.0228. So this probability here, this is 0.022, you can do it, Jeff, 8. So this answer would be about 2.28%. Which kind of makes sense. How many 5'4" guys and below would there be? Not as many, because it's getting a little far away from the mean, right? And now we know officially it's 2 steps down from the mean. There shouldn't be that many men out there. You guys kind of with me? Yeah.
Is there a way to find it without using the chart?
You can find it with the calculator, or you could do the calculus, integrate. Yeah. Yeah. So that's really, this chart came from somebody, actually this chart came from a computer that was programmed by somebody who knows calculus. And they set up the integration, and it came up with these areas. So really, the computer actually calculated the area that's here. Could we do that? No. Look at the shape. What shape is that? It's not a triangle. It's got a freaking little tail and it's curved. I don't know a geometrical formula for that. That's where calculus comes in and says, you don't need geometric formula. I just need a freaking function, and then calculus will eat it up and spit the area out. All right, so if you haven't taken calculus, it's actually really freaking cool. Yeah?
Would you care if we use the calculator integrated?
Oh, set up the formula every time, and then calculate it by doing the integral? Okay, so you have to set that formula up. I mean, that would be kick-ass, because the answers are here, but if you want to, that's I don't mind. Right? Okay. So let's do another one, and then I'm going to have you guys try several on your own. I tell you what, let's do this little lightning round here real quick. I want to make sure everybody can read their charts. So either you have the insert in your book, or you have the back of your book, or you have no book, in which case, just stare at a wall for a minute. See if you can do these problems here. Try to draw the picture first. So probably Z less than 1.28. I like it. So the last one we might have to do together, but I just want to let you try it. If you draw it, you might see what to do with it. Or if you want to integrate it, those are your limits of integration. Gotta be careful. Number 2, it's greater than, so you gotta be careful. You gotta do something to adjust it.
Are we using the same ones like that?
Say again?
Numbers?
Oh, do you see how this is a question about X? So I had to convert it to a Z-score first. These are all questions about Z. So I don't have to convert them to a Z-score. These aren't, I'm not saying somebody less than 1.28 inches tall.
Yeah. Do you just
Right.
want us to draw it? pretty much, or-
Draw it and then find the answer.
That's the
I want to make sure you can use that chart correctly. So if you're really not sure, we're going to do it together in a minute, but just try something. You're not going to turn this in. I'm not going to look at it unless you show it to me, so just try something. Let me make sure everybody's on the right track. Let's look at number 1 real quick. What's it look like? What's right in the middle for Z-scores? 0, I love it. Whatever the mean was for the X score, it always becomes 0 for the Z-score. It's 0 away from itself. 1.28 would be where?
About 0.
Yeah, please, dear God. I always get people just put the damn thing anywhere, but it's so important to put it in the right place because then you can tell if the answer makes sense or not. Right? This is a true number line here. So if it's negative, it's below 0. If it's positive, it's above 0. What area, where would I shade?
Below 128.
I like it. So below 1.2. So I want this area. So I know the answer is going to definitely be bigger than... Bigger than what? It's definitely more than half. That picture is more than half the picture, right? It's way up 1.28 steps up. So it should be a relatively small amount up there, so there should be a big amount down there. Is this one that I can just look it up in the chart and be done?
Nope.
Careful. Yes? Because what's the chart? If I look up 1.28, what's the chart going to tell me? The area that is below. And what area do I want? The area that is below. Okay, good. So if I look up 1.28 in the chart, it will tell me the area that's below 1.28. Isn't that what I want? So then I'll be done. If that's not what I want, I won't be done. So if I look at 1.28,
0.8997.
I like it. So 1.2, and now you got to go over, whoa. That's all I can see. 1.28. So 1.28,
8897.
yeah, 8997. Do you guys see how to read that chart?
Yeah.
I did that a little bit, but you find 1.2, and then you go over at the top, over to 8 as the second decimal place. So they come together, 1.28 is right there, 0.897. You guys see that? This is a really good time to tell me if you do not. So you will have to do this on your own pretty damn soon. Okay. So that means I can put on my chart 0.8997.
8.9%. 9%.
So the answer is going to be about
9%.
89.97% if you want to be that precise. Cool. And tell you honestly, we're going to just start giving probability answers as 4-place decimals, just to match what we get out of here. You can make a percentage also if you want to. I don't care. You guys kind of with me? So that makes sense. It's one step up. It's more than one step up. So there should be a decent chunk of it below that. Sure enough, almost 90% of it's below that. How are we doing? So if your score on a test that is normally distributed is 1.28 steps above the mean, almost 90% of the students score below you. How are we doing? Is that, you with me? So that would be like the percentile, really. You guys see that? 90, you'd be in the 90th percentile for that test. Okay, maybe. All right, so the only difference with number 2, really, the only real difference in idea is that it's greater. So right in the middle is 0. So negative 0.91. It's down there. What area do I want?
Greater than
Greater than.
negative 0.91.
So please, I'm going to point out something that I've been doing, and I'll make sure you guys are with me on this. Notice how z-scores are down here. Percentages are up there. Do you see that? Because percentages and z-scores are evil. They look like each other. So if you put it in the wrong place, you might start thinking about it the wrong way. Probabilities and percentages up here. Z-scores down there. When you look up negative 0.91 in the chart, it's not the answer yet. In fact, somebody may be able to see a shortcut, but don't get there yet. When I look up negative 0.91, what do you get? Negative 0.91. It's right there. Is that with you? So it's negative 0.90, negative 0.91. Yeah. 1814.
It says it in the positive. If you look up the positive.
I like it. So you got the shortcut. So if you look at negative 0.91, where would 1814 go? Does that make sense as the answer?
That's right.
There's no way in hell that could be the answer, right? Because the answer is more than half. So it's down here. The minute you look up a z-score, you could put it down here. And how do you get this side?
You subtract from 1.
Exactly. 1 minus, because it's the opposite that I want. We've learned the damn ideas over and over and over. 1 minus that gives me the opposite side. So 1 minus, don't worry. If you see the shortcut, I'm going to talk about it in just a second. 1 minus that. Do you guys know the shortcut for 1 minus a decimal? Make everything 9, and then make the last one 10. What do I mean with that? What makes 1 9? What do you have to add to 1 to make it 9? 8. So it's 0.8. What do you have to add to 8 to make it 9? What do you have to add to 1 to make it 9? 8. What do you have to add to 4 to make it 10?
6.
There. So that's a shortcut for 1 minus some number less than 1. Or, calculator. You can do other work. Yeah.
It doesn't say that it's 81.86%. Does it only tells us what's below that? Because it's dealing with a negative?
Yeah, the chart tells me it's just because the question wanted greater than. The chart can only tell me less than, because that's the way they set it up. So the chart does as much as it can. If I wanted a chart that did more, it would be its own book, right? Now, the shortcut, what's beautiful about normal distribution is it is symmetric. So the amount of area that's down here, or actually let me say it this way, the amount of area that's up here above negative 0.91 should be the same as the amount of area that's below positive 0.91. So look up positive 0.91. This is exactly what you're saying back there, one. Positive 0.91. What area do you get?
0.81.
Yeah, the answer, 0.8186. Now be real careful. If that chart makes all the sense in the world to you, use it. If it doesn't, who cares? How long was that? Not very. How much, it doesn't save you that much time really, but it's decent to know it. That's kind of... Alright, so finish that last one out. See if you can get that one. That one's... We haven't talked about that yet, but I want the area between two z-scores. So I want you to draw it and see if you can figure out what math you've got to use to get it. If you suck at drawing normal curves, make a triangle, I don't care. You just need some visual to work with, right? So for some reason you can't make that shape. It doesn't have to be perfect. Okay, so what goes right in the middle? 0. And then 1.4 and 1.82, just put them there somewhere. It doesn't really matter. So look at me being all careful now. So where's the area that I want? In between those two, right? Now let me make this really clear right now. The procedure for this could never involve the difference between those z-scores. Because if I subtract z-scores, I've moved where I am. Does that make sense? Those two tell me where I am. If I subtract them, now I'm over there. I got subtracting 0.42. What the hell is that z-score got to do with anything? So it's not subtracting the two z-scores that I want to do. It's probably subtracting something else. Yeah, good. So if I look up 1.4, I'll get this area. I don't want that area, right? If I look up 1.82, I get this area. That's too much for a canary. But if I take the area I get there, minus the area that I get there, I'll end up with that little bit that's right there. Kind of with me. So that's why the visual kind of helps to figure that out. So what do you get when you look up 1.82? What area do you get? Let's see, the 1.82. Yeah, be careful now, make sure it's positive.
9656.
Yeah, 9656. So you get a 9656 there. Is that cool? 9656 here. 1.82. And what do you get when you look at 1.4? What was it? Yeah, 1.4. 9192. So if you just take the difference between those, 9656 minus 0.9192. 0464. I like it. How we doing? Maybe. All right, cool. So let me give you one last problem to work with. and then we're going to head out because my meds are cutting out. I don't know if you can tell, I'm actually sick. But I'll tell you, I'm on a cocktail of medication that's keep me going here right now. Yeah, don't go anywhere with that. That's good. They're all legal. Let's see. So say I have, whoa. I don't want to do something boring like that. Let's see. There's let's do that. IQ scores are normally distributed. And they have a mean of 100 with a standard deviation of 15. So let me give you just a couple to try out here. Now be careful. Again, before you can use that chart, you have to know the z-score, right? So what I write down sometimes is raw score to z-score to percentage. So if I have a raw score, I got to first make it a z-score, and then I can look up the percentage, right? So what's the probability that somebody has an IQ of less than 75? Cool. And then what's the probability that somebody has an IQ more than 133? Try those two problems out real quick, and then we'll call it a day before I fall over. I'll use the key for that. The chart is called the z-score chart. So you have to think that. Yes, exactly.
This is going to be negative. It's going to be
The z-score will be.
the z-score.
Yeah, the actual IQ score is not negative. Yeah, but the z-score will be. Yeah, and you don't even have to know that ahead of time. Then the math will come out when you put the 75 minus. This has always got to be the mean, so that'll come out to be a negative number. Oh yeah, I'll have copies. Yeah, you got it. You gotta be the negative side. Because if you look at the positive side, it'll tell you the area below positive 1.66, which would be way more than what you want. That's why they have the negative side too. Yeah. All right, so let's see. For this first one, if you draw the picture, what goes right in the middle?
0,
Careful.
100.
100. So when you're dealing with raw score stuff, not just z-scores, you put the raw scores as they are, and you put z-scores in parentheses down below, so you know who goes with what. So below that, I can put 0 for z-score. Now I'm interested in the 0.75. That's my data point I'm interested in. And I wonder the probability that it's less than that. So there's my area. So now I got to figure out what to put down there. And what do you get when you do the z-score formula? Yeah, you get, yeah, good. Negative 25 over 15. Yeah, so negative 5/3, negative 1/660. Negative 1.67. Good. Round to 2 decimal places. Notice if you do 6/6, you're going to look at the wrong place in the chart. You're going to lose some points. You got to round to 2 decimal places. And when you look at negative 1.67 on the chart, negative 1.6, I think I got 7.
0475.
0475. So am I done? Yes. Well, how do I know I'm done? Because the answer